Hi everyone, I'm Sang-tae Kim from Information System Lab in Seoul National University. In this video, I'm presenting the semantic-aware superpixel for weakly supervised semantic segmentation. First, I will review some background and I will give you our motivation, and then I will explain how to generate the superpixels, and then the training of the segmentation network. For last, I will show some experiment result and I will summarize. Image semantic segmentation is a task to classify each pixel of input image and has many applications for these days. For data efficient approach, weakly supervised semantic segmentation is widely studied these days. The goal of WSSS is to train a semantic segmentation network using weak supervision. In our work, we use the image level label as a supervision of the semantic segmentation network. A weakness of this approach is that there is no pixel level information in image level label. So in many works, salience maps are widely used as a pixel level supervision for segmentation network, or some work exploit the superpixel as a pixel level information. However, salience map requires the pixel level annotation for training of detector, and the conventional superpixels are too small, so we cannot obtain some useful information from the superpixels. In this work, we propose a superpixel algorithm using the features obtained from the self-supervised vision transformers. In doing so, we can obtain the pixel level information from the VIT, which is trained without any informations. In our algorithm, the main thing we consider is the pairwise feature similarity. We compute two things. One is the similarity, which can be computed as the vector inner product of two feature vectors, and the another thing is the adjacency, which is defined as 1 if two pixels are similar and 0 otherwise. The figure is the example of the adjacency. I only draw the edges between the adjacent pixels, but any pair of pixels can have the same relation. To find the superpixel, we first find the seed pixel of the superpixel. The seed pixel is found by the pixel with the lowest degree. Lowest degree is computed as the sum of all ones of some pixel p. So let's say this pixel is the first seed pixel we found, and then we find the other pixels which satisfies this relation for predefined value tau. So if there is only this pixel satisfying that condition, then we group these two as one of superpixels. So our algorithm is iterative. So we first find the seed pixel and the pixels which are similar to seed pixel, and we remove the found pixels, and we find another seed pixel, and we repeat this process until the all pixels are selected. So this obtained superpixel has a low resolution, so we apply conditional random field to refine the output. Using this superpixel, we use it in generating the initial seed for the training of the segmentation network. From the classification network, we compute the CAM and the CAM score. If the CAM scores are greater than the predefined value alpha, then we assign the class at that pixel. For background region, we find the best superpixel for background. In other words, if the class score of CAM is lowest, then we consider that superpixel as a background superpixel. Indeed, this region seems to be very small, so not enough for training the segmentation network, but our training process can improve the quality of the label, so this is not so much problem. So the segmentation network is trained using the loss, which is defined as like this, and during the segmentation training, since the initial seed quality is not so good, we improve them during the training process using the namely superpixel guided seeded region growing process. So the segmentation output and initial seed and superpixels are all used to generate the refined seed, and refined seed is the final supervision to the segmentation network. So the region growing process is similar to the seed generation. We compute the averaged class score for each superpixel, and if the score is greater than predefined value beta, then we assign the class to that superpixel. If not, we do not assign the class to that superpixel. So the score for this superpixel is greater than beta, so we assign the label here, and the dog is highest, but not greater than beta, so we did not label here. As we train the segmentation network, we can see the refined seed becomes high quality and accurate. We compare our approach to the conventional approaches. In our experiment, we used the ResNet 50 for classification network and ResNet 101 for segmentation network, as done in many works, and we can see that our approach outperforms the other approaches. For more study, we can control the tau in superpixel algorithm. If tau increase, then the image will be segmented into large number of pixels, superpixels. So if the superpixels are too small, then it's difficult to take advantage from that. So we can observe that the final segmentation performance is not good when the tau is too high. We can also control the alpha when we generate the initial seed. If alpha is high, then the seed becomes sparse. From our result, we can see that alpha should be quite high, so initial seed looks very sparse, but even though it's sparse, we have a better performance compared to the dense situation. We can also control the beta when we perform the region growing process. So if the beta is too high, then the score of class score should be high to be assigned to the superpixels. So when the beta is 0.7, we could obtain the best result. As we can see, although we didn't use the salience map in the training of the segmentation network, our network can detect the object with the good boundaries. We also compare the quality of superpixels with the conventional superpixels. We first measure the undersegmentation error of superpixel, which is one of the famous metric in superpixels. So as we can see, our superpixel has a smaller error than other superpixels, and we can also see the number of superpixels is much smaller than others. The next is the achievable segmentation accuracy. As we can see, we can achieve the higher ASA compared to the others. Also, the number of superpixels is much smaller than the others. For last, we compare the boundary quality using the boundary precision and boundary recall. So if we draw the precision recall curve of the boundary, then we can see that our graph is upper right of the others. So in this paper, we have proposed how to generate a spot pixel which is useful to solve weakly supervised semantic segmentation. We have shown that our spot pixel's effectiveness using the segmentation performance and the quality of spot pixels. For the future work, we believe that our spot pixel can provide important information to solve the challenging unsupervised semantic segmentation, and there can be other challenging tasks. So my presentation is over, and if you have any question, please let me know. Thank you for listening and have a nice day.